Hey everyone. In this video, I'm going to talk about interpreting OLS coefficients. And we already talked about OLS and linear regression models for a couple of weeks now. But in the past Q&A sessions, there were still some open questions regarding how to interpret specific model coefficients, particularly if we have logged independent variables or logged dependent variables, or if we have a squared term included in the regression model, and so on, right? And so to be really clear about how we interpret each of those coefficients in each of those cases, I want to go through every possible scenario that we encountered so far, step by step, and really kind of review what we've talked about before and make sure that we are all kind of on the same page as to how we interpret these coefficients, right? And so before I go into different scenarios and different cases, one thing that I want to emphasize in the beginning is that the coefficients and the relationships that we're assessing based on OLS and the coefficients that we're interpreting don't necessarily have a causal interpretation, right? So as we talked about before when we discussed causality, we need additional assumptions to really interpret a relationship as causal. For example, in an experiment where we have random assignment, we can make causal claims. If we have an observational study with some independent variables and a dependent variable that is purely observational, it's much harder to make these causal claims, right? So keep in mind, whenever I'm talking about these regression coefficients, we're talking about statistical associations. They can be interpreted causal in some circumstances if we are able to make additional assumptions, if we know that there are no unobserved confounding factors, and so on. But that doesn't necessarily have to be the case, okay? So keep in mind, we're talking about statistical associations, not necessarily causal relationships. All right, so let's jump into the first case. The first case we're going to look at is a continuous dependent variable, so a continuous y, and we have, in this case, two independent variables, x1 and x2, okay? And in our case here, x1, oops, that's the wrong button, x1 is a continuous independent variable, so y is continuous and x is continuous, and x2 is dichotomous. It either takes the value 0 or 1. That could be in a survey, it could be gender, for example, or dichotomous party identification, or whatever dichotomous factor you could think of in your data set. All right. And so we have the model specification here. Y is our dependent variable. We have our intercept. We have our x1 and the associated slope coefficient, and then we have x2 and beta 2. Beta 2 is the coefficient for the second, the dichotomous independent variable. And I simulated some data here just to give you an example, and I showed basically, based on my simulated data set that I have here, this is the result. Those are the coefficients of a basic LM command. We have an intercept here of 1.78. Beta 1 is 1.17 and beta 2 is 1.95, right? And so this is just one numeric example, and now the question is, how do you interpret these coefficients? What do they actually mean, okay? And let me just go through this step by step, and I will kind of show this in the actual scatter plot, what this actually means in each individual case. So as we talked about before, the intercept, so in this case the alpha parameter, or sometimes you see it as beta 0, tells you the expected value of the dependent variable if all independent variables are at 0, right? So this is kind of this is why we talk about this as the intercept at the y-axis, okay? And to kind of show this visually, we have two variables here, one continuous on the x-axis, x1, we have y on our y-axis, so the dependent variable, and then the blue dots and red dots are observations where x2 is equal to 1, and red dots are observations where x2 is equal to 0, right? And so the intercept alpha describes the expected value of y So this is right here. If all independent variables are equal to 0, which means x1 is equal to 0, that's why we're talking about the intercept on the at the y-axis, or at x being equal to 0. But it also implies x2 being equal to 0, right? So x2 is a dichotomous independent variable that takes the value 1 or 0. So this is the expected value for all independent variables being equal to 0. So for example, if x2 was an indicator for male respondents, then this intercept would be, and our dependent variable was, for example, political interest, then this would be the average expected political interest among female respondents that scored 0 on our independent variable. You know, that might be education, for example. All right, so that's the intercept. Holding all independent variables at 0, then the expected value of y is alpha, okay? And of course, whether this alpha, this intercept, has a reasonable, kind of sensible interpretation always depends on the set of independent variables and what it actually means if those independent variables are equal to 0, right? So in other words, imagine our independent variable x1 was something like monthly household income, for example, or where most households have a positive monthly income or yearly income, for example, and so then the intercept, the expected value of the dependent variable for all the x's being equal to 0, is kind of almost an extrapolation outside of the range of values that we usually see, right? So there could be other, maybe household income is not the best example. Imagine we had an analysis where we compared countries, and one independent variable was the GDP, right? No country has a GDP of 0 or GDP per capita of 0, right? So the intercept then doesn't really have a substantively meaningful interpretation, because this intercept alpha here is kind of outside of the range of reasonable, sensible x values that we actually observe, right? We nevertheless get an intercept, but it doesn't necessarily have a substantively meaningful interpretation. All right. So moving on to the second independent variable, a continuous independent variable x1. We can interpret this independent variable, or the coefficient associate, or the coefficient that is kind of associated with that independent variable beta 1, as holding everything else constant. A 1 unit increase in x1 is associated with a beta 1 increase or decrease, depending on the sign of beta 1, in the expected value of y, right? So in other words, that's the slope of the regression line that we fit in this graph, right? So a 1 unit increase in x, 1 unit increase from increasing x from x1 from 1 to 2, leads to beta 1 increase in y, okay? And so this holds, of course, for both cases where x2 is equal to 0, which is the red line down here, and where cases where x2 is equal to 1, that's the blue line up here, right? So in both cases, we see the same increase in y that is associated with a 1 unit increase in x, okay? And that's beta 1, okay? All right, lastly, our dichotomous independent variable x2 can be interpreted as an intercept shift, right? So we have our regression line that is kind of fitted through these observations, and then our beta 2 can be interpreted as holding everything else constant. The expected value of y is increased or decreased by beta 2 when x2 is equal to 1 instead of 0. And so what that means is that we have this regression line for x1 equal to 0, and if x1 is equal, for x2 being equal to 0, and for x2 being equal to 1, then this regression line is shifted according to beta 2. Right? And beta 2 here is 1.95, so this regression line is shifted almost 2 points And we see that shift right here. Right? So that's the interpretation of our dichotomous independent variable. And now, note as I mentioned before, that this, while the line is shifted, the slope, so the relationship between x1 and y, is equal between both groups, right? So the slope of those two lines is the same, okay? So no matter the value of x2, beta 1, or the effect of x1 on y is constant, okay? Of course, there might be cases where this might not be the case, and in order to take this possibility into account and basically consider the possibility that these slopes differ between those two groups, we need to include interactions. So in the next video, I'm going to talk about interactions that are included in addition in that model, and how we interpret those interaction coefficients that we talked about in previous weeks as well. All right, but I'll take a break here and continue the next video with this second case, interactions.